Okay, so let's just start the discussion right now. The next lab is going to focus on, is going to focus on heat transfer, which is true for this lab and the lab after this one. So we're gonna spend 2 labs on the heat transfer. Have you guys taken a heat transfer course?
No, I'm currently taking it.
You're currently in one. So I guess we talked about this, right? Yeah, I asked you the same question on Tuesday. But we are going to cover whatever you need to know to write the lab report and do the experiment. And the idea is for you guys to become a little more familiar with 2 different types of heat transfer, conduction and convection, which are the most common ones in mechanical engineering analysis and aerospace engineering analysis. If you end up being involved in the space industry, then you want to know a little more about radiation as well, because in the outer space, the radiation is the most dominant heat transfer, and is actually one of the important parts of the design of a spacecraft. But in general, heat transfer is a very important, yes.
I want to ask, are we going to focus on forced convection or natural convection?
Both, essentially. We're going to see. I will talk about the lab at the end of the lecture. Okay. I tried to keep this lecture short as possible, the same as the previous lecture, like two weeks ago. And I essentially just want to talk about the necessary stuff that you need for the lab. But I will upload the whole lecture notes, so you can go ahead. But we are going to focus on both sides. Which chapter are you in your heat transfer class right now?
We're in chapter 2 doing thermal diffusion right now. We finished everything up then, so it's still chapter 2.
So you haven't done any convection yet?
We did like the basics at the beginning for the first convection, radiation.
Okay, that doesn't really help that much, but yeah. Heat is the only one who teaches the course at this point. I mean, I used to teach that course myself. I like to teach it more, but we have so many aerospace courses. And we don't have any instructors. They asked me to teach a design course. It doesn't make any sense to me, but I guess we are recording now. That's what was I saying? Okay, so we are gonna cover the basics. We are going to talk about the theory, talk about the lab, and then next week we are gonna do the conduction experiment. We're gonna do the conduction theory, and the week after we're gonna do the wind tunnel. This is going to be your last lab. Afterward, you need to focus on your presentation. Okay. Just a quick reminder, since I'm recording this and I want others to see this if they are watching. We had a discussion with one of the students about the grading. If you have a problem with the grading, you always have to bring it up to me. You have to come to my office, bring your report to my office, or send me that specific report that you're talking about. Then we can discuss the grade. A general discussion about the grading doesn't really help you or me, right? I don't know if I should increase your grade or decrease it. Does that make sense?
No.
Okay. It is. I mean, having questions about your grades is always a valid question. You should always bring. If you are not satisfied with your grade in any way, you should always bring it up with me, right? And since I don't grade the lab reports, I cannot answer any questions on the top of my head. I should look at the again. I should talk to you here. Okay, so okay, so let's do this. Let's see. The first thing we want to discuss is what is heat transfer in general. The name itself is very self-explanatory. Heat transfer is a thermal energy in transit due to a temperature difference. So the main part of the heat transfer is the difference in temperature, right? Between 2 different surfaces, between 2 different conditions, it can be 2 different planets, it can be 2 different surfaces, it can be a surface and some fluid on top of it, right? But there must be a difference in temperature. The next thing we want to explain and we want to understand the meaning of is the thermal energy. Thermal energy is associated with the translation, rotation, vibration, and the electronic state of the atoms and molecules. So when we refer to the thermal energy, we are essentially referring to the energy of the bulk of molecules, right? Which means that when your medium has higher thermal energy, it essentially it says that your molecules are vibrating more, right, or moving faster, or whatever, right? And which translates later on to temperature, right? So thermal energy in general represents the cumulative effect of the microscopic activities and is directly linked to the temperature of the matter. Before this is an introduction, what I didn't cover, which is also in the lecture notes, you can always go back and see, is that microscopic look at the heat transfer, which is called the theory is called the kinetic theory at the fluid heat transfer. It's called the kinetic theory of gases, right? You can always go over those part of the lecture and you can ask any questions you have from me. But we don't really care about those parts in our test, so let's decide to forego it. We have different modes of heat transfer. So at this point, we are familiar with what heat transfer is. We know what thermal energy is, and we have a rough understanding of temperatures, right? Let me make sure we have the rough understanding. How would you define temperature of a medium?
Temperature of a medium?
Yeah, whatever. Temperature of a fluid, a solid, or
temperature is the vibration of the molecules. The higher they vibrate, the higher the temperature.
That's a state of the energy of the molecule, not necessarily just the vibrational energy. It is also the translational, rotational energy, right? Higher energy state, higher temperature, higher bulk temperature. But keep in mind that the temperature, we do not define temperature for each molecule. We define temperature for the bulk of the material, right? So you should have to keep that in mind. So we have three different modes of heat transfer. The first one is conduction. Heat transfer, conduction is heat transfer in a solid or a stationary fluid. Okay, so fluid or gas or liquid due to the random motions of its constituent atoms, molecules, or electrons. Right. So the most important part that you want to keep in mind about conduction is that conduction refers to the transfer of heat in a stationary state, right? So essentially you have two energy levels, two temperature. Let's think of a wall. On one side of it you have one temperature, on the other side you have another temperature, right? Like the temperature difference between the inside of this room and the outside temperature, right? Because of that difference in energy state, the higher energy wall, part of the wall, is actually transfers its energy to the lower energy part of the wall, right? Through the vibration. It's a solid, so we only have the vibrations at the place. There's no translation, there's no rotation. It's a solid, right? So the one molecule starts vibrating because of a higher energy, then it transfers vibration to another molecule, and so on and so forth till the energy gets transferred through the wall.
So that's basically like how flowing to cold.
Basically, like what?
Like how heat flows to colder.
That's it. That's the idea. Yeah, that's the idea. As long as we are talking about a stationary transfer of heat, that's essentially it. Okay? Yes? Okay. So moving on, convection is a transfer of the heat due to the combined influence of the bulk and the random motion for fluid flow over a surface. So there are a couple of important points here. Is that the convection only applies to a fluid flow, right? Solids don't flow, so solids are not included in convection. The only thing that really flows is the fluids, right? Gases or liquids. And we have two different parts of the convection that we will discuss a little bit later, that the bulk transfer of the heat and the random motion transfer of the heat. We'll discuss them later on. And the other part is that this convection is happening usually over a solid surface, which means that you have a solid surface that has a specific temperature or heat flux coming through it, and then you have a different temperature fluid on top of it moving, right? That's when you have convection. Yeah? The convection analysis is actually a very important analysis when you are dealing with when you are dealing with a space reentry applications or any type of aerodynamic heating.
No, I was just gonna say, like, wouldn't that apply with like wings and having the ambient temperature at the top and the fluid flow rate, and as well as the temperature of the wing itself? Like how they pump the fuel through the wings to be able to take advantage of that.
Exactly. So that's the thing. That's a very good. So you're essentially preheating the fuel or use the cooler fuel. That there are the heat transfer in aerodynamic applications is a very useful application, and for whatever reason, most of our people here are not heat transfer people, so we don't do that many research in aerodynamic heat transfer. But you can actually using cooling or heating the aerodynamic, you can change the stall conditions of a wing. Right, this is a very important parameter when you are designing an aircraft, right? And the problem with that is that you have to provide a cooling or heating medium. You have to create a cooling or heating medium inside the wing, right? And that may create problems, right? You may add weight to the wing that you don't want to add, or other structural problems, right? So there's always a compromise somewhere, right? But it is a well-known fact that the heat transfer will change the your aerodynamic design. And yeah, I mean, when you're dealing with fluid mechanics in general, you always have three sets of equations: conservation of mass, conservation of momentum, and the energy equation, which refers to the heat transfer, right? Okay. And the last part of the heat transfer, the last mode of the heat transfer that we want to discuss here is the radiation, which is the energy that is emitted by the matter due to the change in the electron's configuration of its atoms or the molecules, and is transported as electromagnetic waves or photons, right? It depends on actually that gets to a little more physics part of the stuff when you're dealing with radiation. And we don't have any radiation course in this department, so you can always go to the physics department and take a course over there if you are interested in that. But the modern physics comes into play here. It depends on your perspective. Do you think of light, or do you think of light as particles, or do you think of light as waves, right? That comes into play in the discussion of radiation. But as far as we are concerned, we only care about the equation that we are using as far as it comes to radiation. Is there any questions so far? There is another type of, there are other types of other modes of heat transfer. But these are the three main ones that we really care about in mechanical engineering or aerospace. And mechanical and aerospace engineering are essentially very similar to each other. Huh? Aerospace is a specialized type of mechanical engineering. That's why I usually use the more general term. So can you guys think of any other type on other mode of heat transfer other than these three? So heat transfer through solid or stationary fluid, heat transfer through moving fluid, and heat transfer through waves or photons, right? Just think about it. Essentially, we are trying to find any form of energy release that is not covered by these three, or energy transfer that is not covered by these three. There is one very important form that is actually very important in aerospace applications as well, but we don't care about that part of it, and that part of the analysis. Think about it. What is a very important part? What is a very important energy release mechanism in aerospace industry? Or energy transfer mechanism?
This has to do with combustion.
Propulsion, right? So essentially, you are dealing with combustion or chemical reaction, and the chemical reactions are not covered with by any of this, right? That's the energy release because of not the changes in energy state of a specific molecule, but because of the reaction that is happening, right? And we don't really talk about the chemical kinetics in general or the chemical reactions in mechanical and aerospace engineering. That's why it's not covered here. and it is not covered in the heat transfer course as well. Yeah. But let's dive a little deeper in the conduction and see what we are dealing with. Let's try to theorize it and find the theory behind it. So we define the conduction as the transfer of energy from a more energetic to a less energetic particle of a substance due to interactions between the particles. We quantify the heat transfer rate as the amount of energy transferred per unit time, and we actually find this heat transfer rate using the Fourier's law. Do you remember what the Fourier's law was, Igor?
Sounds familiar, but something I can define it.
Okay, the Fourier's law of conduction is actually the most important part of the heat transfer analysis, other than the energy equation and the partial differential equation, right? And it is a law that we have never proved mathematically. It's just it's based on the experiment, right? It essentially tells us that the heat rate, let's say we are dealing with a solid slab with like a wall with two different temperatures on the both sides, right? It essentially characterizes the heat rate that is passing through this wall, or the energy transfer from this temperature to this temperature, right? As a function of conductivity of the wall, which is the ability of this wall to transfer that amount of heat, right? And the temperature gradient, right? So the rate of change of temperature, right?
So is that just Q equals negative K times area of PTDF?
That's it. Or in more general terms, in more dimensions, the 3 dimensions, you can just say that your heat flux, which is heat rate, total energy per unit area, is equal to negative K, the gradient of temperature, right, in each direction. So that's going to be your Fourier's law. And we are going to focus on the Fourier's law in the next lecture, because that will be the topic of the second heat transfer experiment we are going to have. But can you think of why we have the negative sign here?
Based on the direction of which the heat transfer rate is going into?
Yeah, it is exactly. That's the direction. So essentially, this negative sign is telling us that the heat is in the direction of a state 1 to a state 2, not the other way around, right? So you essentially, to find the correct direction, you essentially find the delta T first, which is usually T2 minus T1, but T2 is always smaller than T1, right? So you have to have a negative sign. That's a convention, right? That's just some convention. But let's try to simplify this equation for this slab. This is a one-dimensional slab. There's one-dimensional heat transfer, which essentially tells you that the heat transfer in every direction is just heat transfer all over the wall is just in the x direction, right? Because the wall is so long that the heat transfer in the other direction is negligible. Meaning that the main temperature difference happens in the x direction, not in the y direction. Does that make sense? Okay, so if you try to simplify that, we can essentially say we only have the x temperature derivative, right? So your heat flux in the x direction is going to be negative K dt dx. Then if there is nothing special happening inside the wall, meaning that there is no heat generation, there is no explosion happening inside the wall, there is no wire passing through the wall, there is no heat generation inside the wall. We can simplify this derivative term to delta, so it's going to be delta T over delta X, which in this case is going to be T2 minus T1 over the length of the wall, the thickness of the wall. Yeah. And then you can bring the negative sign into the equation and can have the total heat flux to be equal to K, T1 minus T2 over L. Is there any question? Yes.
So does that mean we're only dealing with one-dimensional flow for these experiments?
For the next experiment, not for this one. Yeah, it's true for this one as well, but we don't do conduction for this experiment.
Okay.
So we'll get there. Okay, but so far we have only calculated the heat flux, and heat flux is the heat transfer or heat rate per unit area. Okay. So that to calculate the total heat rate that's passing through the wall, or total energy that is being transferred through this wall, this huge wall, you just have to multiply the heat flux by the area of the wall, and that is the area perpendicular to the direction of heat transfer. So this area, okay, the cross-sectional area. Does that make sense? Okay. So let's move on to convection. The convection, we define convection as the heat transfer due to the bulk movement of molecules within the fluid, such as gases and liquids. Convection includes two sub-mechanisms. We have advection and diffusion, right? And we usually block them together and only do the convection analysis. We don't do advection and diffusion separately in this, at least in this lab, and also in the heat transfer course. But advection is essentially the directional bulk flow transfer of the heat, which essentially means that, let's say you have some fluid here, and you're heating the fluid up, you're heating up the fluid, like in a pot or whatever, right? There is this bulk of fluid that's getting hotter, and the bulk itself moves to the higher surface, because of the density change, right? It moves to the top, and then a bulk of cooler fluids replaces it, right? That will be your advection. But the diffusion is essentially each higher energy molecule moving and colliding with another lower energy molecule, right? And transferring the energy to that lower energy molecule. Does it make sense? Okay, so we have these two mechanisms, but we always combine them together and study them together. The convective, so in this case, instead of the conductivity of a material, we have the convective. Is it your phone?
Yeah, it is. I'm gonna put it on silent.
Why don't you?
I forgot. I usually have it on silent.
Oh, that's right. Okay. So the convective, instead of having a conductivity, we are going to have a convective heat transfer coefficient. The difference between a convective heat transfer coefficient, which we use the term H for it, and conductivity is that conductivity is a material property. Like the conductivity of wood is different from a plastic, is different from composite, and composite has different conductivities in different direction, but it is still a material property, right? The conductivity of steel, and we usually assume that it is independent of the temperature, right? But the convective heat transfer coefficient, or H, is not necessarily a material property, but it depends on a lot of things. It depends on the temperature difference. It depends on also the material. It depends on your geometry. It depends on type of the fluid. It depends on a lot of different things, right? So it is definitely not a material property. It is let's call it a situation property, right? It depends on your situation. And this is something that you have to calculate yourself. You cannot just measure the conductivity of air, the heat transfer coefficient of air on some surface and say this is the heat transfer coefficient of air everywhere. Okay? And to be able to characterize this convection, we have the Newton's law of cooling. Okay. And using the Newton's law of cooling, we can calculate the heat flux, which is, again, we have a sign convection for this. That this heat flux will be positive if the heat is transferred from the surface to the fluid, meaning that the surface has a higher temperature, so you're essentially heating your fluid, and it's going to be negative if your surface is cooling the fluid. So essentially the heat is being transferred from the fluid to the surface. Okay. So do you remember what the Newton's law of cooling was?
The H sub C times area times the change in temperature.
What is that law for a heat, for the heat flux?
Oh, for the heat flux, you get rid of the area because it's lost.
That's it, exactly. So essentially, Newton's law of cooling in general is going to be your heat flux Q del prime is going to be equal to your heat transfer coefficient multiplied by the surface temperature minus the fluid temperature. Okay. Here in this table it is not legible, but I have a table here. You can go back to the lecture notes and check it out. We have the ranges of heat transfer coefficient for some examples of liquids and gases in different types of convection. See, so this tells you that the convective heat transfer is a function of many different things. Whether what is your fluid velocity? Is it the forced convection? Is it free convection? Or what is your temperature, and so on and so forth. Is there any questions so far? No. Let's do the radiation. Radiation, we define radiation as the emission or transmission of energy in the form of waves of particles through a space or through a material medium. Okay. So let me ask you this. Let's talk about this last part, the through a material medium. Can we have radiation through solids?
Yes.
How? Or yeah.
Radiation it depends on the particles as well, right? Alpha, beta, gamma.
We are talking about the radiation heat transfer. Okay. So that's a little more general than just about the different energy levels of different particles with different energy levels.
So you can pass through any medium, right?
It can pass through any medium, but passing through a solid, the radiation heat transfer through a solid is less intuitive. It is hard to comprehend, right? And why is that?
Because on such a small scale, like you can't really visualize it that well.
So that's the idea here. You think of the solid as a solid slab, right? A continuous surface, but in reality, it is not a continuous surface, right? It's just different molecules that are bonded to each other. So the energy can be transferred through radiation to a solid medium, but the conduction inside the solid is so dominant that we don't really care about the radiation, right? It doesn't really matter the radiation inside the solid. So the radiation is way more dominant in a vacuum or in gases. So even in fluids, radiation is not that. In liquids, radiation is not that important. Does that make sense?
That's mostly negligible for our purposes here.
Yes, for our analysis here, it is mostly. I can make it now a little more difficult and ask you to calculate the effects of radiation. But I guess I'm not going to do that. But so the radiation includes the electromagnetic radiation, particle radiation, acoustic radiation, gravitational radiation. Thermal radiation, which is our topic, which is our focus, is the energy emitted by the matter at a finite temperature. Radiation that is emitted by the surface originates from the thermal energy of the matter bounded by the surface, and the rates at which energy is released per unit area is termed the surface emissive power. Okay. And there is a maximum to this emissive power of each surface. Does anyone know what is the maximum? Or what is the upper limit to the emissive power of each surface? What is the maximum emissive power in general? What is that specific body that can emit or absorb the most energy? Or light, or different energy particles?
I'm not trying to understand the question.
I don't know how to say that a little more clear. What is that? What kind of medium absorbs the most energy, or light, or like any particle, or like different types of waves?
Solid.
Solids absorb more than gases, mainly because there is more concentration of the molecules, right? Because you need to have a molecule that absorbs the energy, right? There should be something. In a vacuum, there's no energy absorbed, the energy just transfers. Okay? Think about it. What is it in the world that they say, what is it in the world that light doesn't pass through, or there is no reflection of the light from?
Probably like black holes or something.
Okay, black holes. What is so specific about black holes?
That their density is extremely high. That's probably why, like you were saying, like with the solid material, there's a lot of things it can contact with, and the density of an object.
Okay.
Gravitational pull has a lot to do with.
Gravitational pull of the black hole.
Yeah, it absorbs everything. Nothing escapes from it because of gravitational pull.
Well, why is the gravitational pull so high?
The density.
So essentially, what it comes to is that we call this ideal type of body that absorbs all the energy that comes to it, or releases all the energy that it can release, as a black body, right? Have you heard this term before? I think so. You should have heard it in your physics class.
Black holes? I don't know black holes.
No, not black bodies, not black holes.
No.
Okay. That's right. So, but that's the upper limit of the emissivity you can have, right? And that can be characterized as the epsilon E of that's an E of B. This is the energy emissive power of the black body. This E of B, which can be characterized as sigma, which is the Stefan Boltzmann constant. Yes.
But if you normally have two temperatures, like a T1 to the 4.
We are talking about we are only talking about the emissive power at this point. Okay. Right? We are not talking about the absorption. We'll get there in the next slide, right? So the maximum power you can get out of the maximum emissive power you can, maximum energy emissive energy you can get is epsilon multiplied by Ts, the surface temperature, to the power of 4. But then it means that for any different type of material or surface that is not a black body, which includes everything, right? We are going to have a smaller emissive power. So to be able to characterize that, we have defined this new term, emissivity, right? That essentially compares your emissive power of each body to the ideal case, which is the black body, right? So emissivity of 0.9 means that you can emit 90% of the most energy you can emit from that specific surface with that specific temperature. Does that make sense? Okay. But we have another, when it comes to radiation, we have another type of energy. So far we have talked about the emissive power. What about the absorption? Some energy can be absorbed by each surface as well. And for that, we essentially have the same theory and same ideals. The only difference is that the non-ideal part of your absorption comes from alpha or absorptivity instead of emissivity, right? In most cases, and the maximum absorption you can get on a surface is actually a function of your surroundings temperature, right? So the maximum absorption this table can have is the absorptivity of this table multiplied by the temperature of these walls, right, to the power 4, right? So that's a characterization. So the maximum radiation you're going to have from a surface is essentially a subtraction between your emissive power and the absorptive power. Okay? And we usually assume that the absorptivity and emissivity are equal, so you'll end up with this equation. The emissive power, epsilon sigma T to the 4 minus epsilon sigma T surrounding to the 4. Okay, and this is the famous equation that you either have seen in the heat transfer course or you will see if you end up taking the course. But this equation doesn't look anything like the other equations we have seen. So to make it a little more similar, we define the radiation heat transfer coefficient as this, which is just mathematical manipulation of whatever you have, right? We define the radiation heat transfer coefficient as this, and then your total radiated heat flux can be calculated as H of R Ts minus T surrounding, multiplied by Ts minus T surrounding. And this is very beneficial when you're dealing with a combination of convection and radiation, because then you can actually compare H of R and H and see which one is more dominant, which form of heat transfer is more dominant in your specific case. Okay. Is there any questions so far? No? Okay. Let's talk about the steady state condition and the transient condition. We talked about the steady state and transient conditions as far as the fluid flow is concerned in the previous lecture, if you have watched the previous lecture. And I'm pretty sure at this point in your educational career, you already are familiar with the steady state and the transient condition. A steady state condition is actually, let's actually go by this. So let's do this. The system that is characterized by a steady state condition. It states that the temperature at each point doesn't change with time, right? So essentially, you will have a stable temperature difference, temperature gradient. Think about this. Think of, let's say you have a solid slab, you have a heater and a cooler on both sides of the solid slab with constant temperatures, right? After some time, there will be a temperature gradient, a constant temperature gradient inside that block that won't change over time. That is an example of a steady state heat transfer. So the temperature inside your domain doesn't change over time, right? It is very simple, but we are usually dealing with one-dimensional steady state heat transfer systems here, but it can represent a lot of different conditions that you will see. But there are other cases that we cannot use the steady state, so we have to apply other methods. And this is one of these other methods is the thing that we are going to do in the next lab on Tuesday. Okay. The transient conduction. Many heat transfer problems are time dependent, and which essentially means that the temperature changes over time at your boundary or wherever. But the experiment we're going to do on Tuesday is essentially an example of transient conduction. We are going to have a sudden change in the surrounding temperatures of a proper block. I will explain it a little more later on. And that sudden change will cause the temperature change over time. Have you gone over the lump capacitance method?
I'm not sure.
I don't think so. But it is at the end of the semester, huh? Okay. Don't care about that. So, to be able to analyze this type of transient conditions, we have this method called the lump capacitance method. That the lump capacitance method, the first thing you do when you're dealing with the lump capacitance method is actually compare. Let me actually use the board a little bit. Let's say you have this liquid pool at a specific temperature T infinity, and you have a ball, a solid ball, at a different temperature Ts, right? And you just drop the ball inside your liquid pool, right? These two temperatures are different, right? So you will see a heat transfer inside the ball. But what is going to happen first is that the first part of this ball that is going to be affected are the near surface parts, right? So the near surface part will have a temperature that is not equal to T infinity, let's say T infinity is larger than Ts, right? So essentially you are heating your. So these temperatures are smaller than T infinity, but still larger than Ts, right? So if you go inside a little bit, you will have other temperatures that are still larger than Ts, but smaller, let's call it T2, T1. But smaller than T1 and smaller than T infinity, which tells you that there will be a temperature gradient inside this solid ball. What mode of a heat transfer does this remind you of? The temperature gradient inside of a solid ball. The conduction, right? Okay. But we also have heat transfer outside of the ball, right? What mode of the heat transfer does this remind you of?
It's convection goes to fluid.
Convection, exactly. So we have convection, we have both of them, right? And it is a transient case. So this actually is a very complex system to analyze. But this lump capacitance method tries to simplify this type of system. The lump capacitance method assumes that your conduction is happening so fast that the temperature inside this solid ball is always not at Ts, but is always changing and it's always uniform, right? So the temperature here is T as the same as temperature on the surface. Does it make sense? So you are essentially removing the temperature gradient inside the solid ball, which means that you won't have the conduction anymore, right? You won't have that one-dimensional heat transfer, right? It will be a one-dimensional polar heat transfer, but it's a one-dimensional heat transfer nonetheless, right? So if you can apply this lump capacitance method, you only have to deal with a very simple convection. The only catch is you have to be able to calculate a heat transfer coefficient, right? And that is what we are going to focus on, is calculating this heat transfer coefficient. Okay, so long capacitance method, but there will be two types of convections that we are going to deal with. One is going to be the free convection, the other one is going to be the forced convection. The natural or the free convection is essentially is a type of heat transfer in which the fluid motion is not generated by any external source, like a pump, fan, suction, or but is only there because of the density change, right? So when you have different density in fluid, you will have some very small motion, but it is going to be there, and that's where your convection is happening. So essentially, let me give you an example. Let's say you have a block of ice, small block of ice, you put it on this table, right? The temperature of the ice is going to be smaller than the temperature of the room temperature. So it's going to start melting, right? And that melting is actually another mode of heat transfer that we will discuss. Because of the air temperatures close to the ice block is going to be smaller than the air temperatures here, further away from the ice block. That temperature difference will cause a density difference, and that density difference will cause some sort of motion, right? And that motion will increase the heat transfer by itself. Does that make sense?
So it's the concept of diffusivity you mentioned earlier, right?
Yes. Yeah. It is a combination of the two, advection, because you can have both movement of air as well.
Right.
Okay. But the main part that you need to keep in mind is that you are going to deal with the buoyant forces a lot, right? Buoyant forces become very important because you will see the density difference. Does that make sense? Okay. I guess we talked about this. We also talked about the buoyancy, but there are a couple of non-dimensional parameters that are become very important in the natural convection that we'll talk a little bit about, a little more about in the next slide. The first one is the Rayleigh number. That is going to determine the onset of natural convection. The second one, which is the Grashof number, which is going to characterize the tendency of a particular naturally convective system towards turbulence. And we talked about the buoyancy. And whenever you use a fan or a pump to induce fluid motion, let's say we are talking about that block of ice here again, and then we have a fan that is blowing air on top of this ice, right? The heat transfer mechanism is definitely going to be different, and that is your forced convection. Okay. There are a couple of important non-dimensional parameters. We talked about two of them, the Grashof number and the Rayleigh number. We don't see the Rayleigh number here. We're going to see it later on. But here I just have a combination of all the important numbers. So the most important is we need to analyze whether the lump capacitance method applies to our system in the test, right? That's where the Biot number comes in. You're essentially comparing the heat transfer coefficient, the convective power of your system, to the conductive power of the solid, right? So heat transfer coefficient multiplied by the length of the system, length of the fluid, divided by the conductivity. And we are assuming the conduction happens so fast that the temperature of the solid is going to be uniform all throughout, which means that your conductivity is much, much stronger than the convection because it happens so much faster. Does that make sense? So in order for your lump capacitance analysis to be true, lump capacitance assumption to be true, your Biot number must be very small. That's the idea. And we usually use the cutoff limit of 0.01. Some people use 0.1, 0.01. But the point is it has to be very small. Then the Grashof number that we discussed, we will discuss a little more. It is essentially measure the ratio of the buoyancy forces to the viscous forces. Then we have the Nusselt number, which is also a very important dimensionless parameter when you're dealing with the convection. It is the ratio of convection to pure conduction heat transfer of a fluid. So the equations of the Nusselt number and the Biot number look pretty similar, but the difference is here, you are in the Biot number analysis, you are comparing the convective power of a fluid to a conductive power of the solid that is immersed in that fluid, right? But for the Nusselt number, you are comparing the convective power of a fluid to its own conductive power, right? When it's at a stationary condition. Does that make sense? Okay. Then we have other non-dimensional parameters. We have the Prandtl number, we have the Teklet number, and we also have the Reynolds number, which are very, very important. But I'm assuming you have seen the Reynolds number before. The Prandtl number is essentially measure of the dominance of momentum diffusion versus thermal diffusion. So which one diffuses faster, the momentum or the energy of the system? But in our case, we are just going to we are only dealing with air, so the Prandtl number in our case is going to be 0.71. That's it. That's all you need to know at this point, as far as it comes to the Prandtl number. So let's talk a little bit more about this equation. The Reynolds number is an important dimensionless quantity. In the fluid mechanics is the ratio of the inertial forces by the viscous forces. So if you have a higher Reynolds number, it means that your inertial forces are more dominant, and that essentially identifies the onset of turbulence for you guys. We can characterize different types of flow. We are a very low Reynolds number flow is called the creep flow. It is a very viscous dominated flow, so you cannot assume any inviscid condition for that type of flow. And we talked about the Nusselt number in detail. It's a compare of the convectivity transfer to the conductivity transfer of the fluid. That's very important, right? So this is the conductivity of that fluid. And I guess I'm just going to skip over the Prandtl number. You can always go ahead and read through this slide here, but I don't think you really need to concern yourself with as far as the Prandtl number goes is that it is 0.75 in the equations that you want to use. The Grashof number is a very important number when you're dealing with natural convection. Approximate the ratio of buoyancy to the viscous forces acting on a fluid. So essentially, it's analogous to the Reynolds number when you're in the forced convection system. In a natural convection system, we don't really calculate the Reynolds number. I mean, we're going to get there, but the most important characterization of the natural convection is going to be your Grashof number. It is customary to define the Grashof number as the square of the Reynolds number. So essentially, in a natural convection, if you were to calculate the Reynolds number, you have to calculate the Grashof number and then take the square root of it. Does that make sense? Okay. It is a way to quantify the opposing forces of the buoyancy and the viscosity. We can calculate the Grashof number using these equations for different types of shapes, right? For a vertical flat plate, it can be calculated as G multiplied by beta. Let me rewrite this. That's G multiplied by beta multiplied by your delta T, which is T fluid minus T infinity squared, right? L squared. And actually to the third. Divided by the viscosity, kinematic viscosity squared. That is for a flat plate. But if you are dealing with a sphere or some sort of non-flat plate, a circular plate, you have to d to the third over nu squared, kinematic viscosity, and any type of bluff body that is not a flat plate, you have to use the same equation as the circular one. Just have to find an equivalent diameter. But our experiment is actually, we are going to use a flat plate, so you don't need to worry about any of the things. And the only thing that you really don't know here is the beta, which I don't know if it's legible or not, but it's a coefficient of thermal expansion. And for our case, it is 1 over TS, the surface temperature. And these are all TS's, not TS. But it doesn't matter. That's the surface temperature or the fluid temperature that is adjacent to the surface, which is supposed to be the same. Okay, then the next part of the natural convection analysis is the Rayleigh number. We define the Rayleigh number as Grashof number multiplied by the Prandtl number for a flat plate. So it's G beta Ts minus T infinity over nu alpha multiplied by L to the third. And the Rayleigh number for you, another number, or we can actually use the combination of Grashof or Rayleigh and Reynolds. Another number that becomes important for us is the Richardson number that is going to tell you whether you have natural convection is dominant or forced convection is dominant. Which one is more dominant, right? If your Richardson number is smaller than 1, your free convection can maybe neglect them. If it is equal to 1, then you have to include the effects of both natural and the forced convection. And if it's larger than 1, forced convection can be ignored. Okay. Well, let's talk a little bit about the experiment and then we'll be done for today. Let me actually go over the copper blocks first. So we are gonna use this type of copper block that is going to be connected to a thermocouple to measure the temperature of the surface in our analysis. What we want to do is essentially put this copper block. The first thing you want to do is to measure the dimensions of the copper block, and calculate the surface area and the volume for your analysis. Then you want to open the lab view to measure the temperature of the surface, right? The next thing you want to do, we are going to give you some electric kettles to boil water. You have to boil water essentially and put the copper block in it until its temperature reaches 80 degrees, right? 80 degrees Celsius, okay, the copper block temperature. So you have to make sure that your water is already at boiling condition, is at 100 degrees, so the copper block temperature will definitely get to the 80 degrees. Then you pull the copper block, you pull the copper block out and dry it using a paper towel, because we only want it to be exposed to air, not any other type of fluid. Okay, and then we give you a stand. You put that over a stand, and you start collecting the temperature. What do you expect to see? You expect to see the temperature to drop, right? Does that make sense? Because the room temperature is definitely less than 80 degrees. Otherwise, you couldn't stand the temperature inside the room. Right? 80 degrees is so hot. It's like 200 Fahrenheit, something like that. If you're not familiar with Celsius, it's like around 200 Fahrenheit. What's that?
No, people can withstand. They go to the sauna, it's around the temperature. But only for a living.
Maybe for like 2 minutes, and then you're like too hot.
You stand there for a couple minutes, and you'd be surprised.
I guess you can stand it, but the room temperature in the lab is not going to be 80, so your temperature will be dropping. Okay, but I mean, Nirla brought up a good point. You always go to the sauna, and it's, I don't know if it's 80 degrees temp though. Like it should be 60, 50.
In Fahrenheit, it's usually 180, but they can go up to 220. I heard. I never been to one, but
220. Yeah,
that's just crazy. But if you're like one of the normal people, you go to like 180. Some people do 200, but they don't go higher than that.
Okay, that's interesting.
But it's like 10, 15 minutes, not more than that.
Yeah. Well, in our case, your temperature will drop, right? And then you collect the temperature versus time until your copper block temperature reaches 50 degrees. And you collect and save the data for the analysis to find the heat transfer coefficient. Okay. And then we repeat this stage 3 to 5 exactly the same. The only difference is going to be that you are going to have a fan that is going to blow over your copper block, right? So essentially you're comparing the forced convection and the free convection. After you calculate the heat transfer coefficient, you have the copper block's conductivity, right? You have to see whether the assumption that you have the lump capacitance method is correct or not, is a correct assumption or not, right? So you essentially can calculate the Biot number for that specific case after you have calculated your heat transfer coefficient, and we will discuss how to calculate the heat transfer coefficient in the lab, right? So I'll definitely come to the lab myself, or I'll make sure Surab shares that information with you. And we'll definitely go over it. But there is another way of calculating the heat transfer coefficient for your specific case, and that is to calculate the Nusselt number using the experimental correlations you will have. We have different correlations for different types of conditions, especially when it comes to the natural convection. Your correlations are going to be much different, right? I have different correlations listed here, which you cannot see on the projector, but it is in the lecture. So you make sure to go over there. You have to calculate the Reynolds number. You have to calculate the or the Grashof number for the free convection part, and then you can calculate the Nusselt number. From that Nusselt number, you can calculate a heat transfer coefficients. Okay, and that's it.
So, I actually have a question. You said you get points for attendance as well in the labs?
That's 20. So have you seen the syllabus? I guess not very carefully. So let's bring up the syllabus. Let me just stop the recording here.